set up for a remarkable, inestimable occasion not too far off. A major purple monstrous huge star at the edge of our world is discharging strange cautions all through the universe. Using the James Webb Space Telescope, stargazers have made disrupting revelations around this enormous heavenly body. Eminent astrophysicist Brian Cox gives a serious admonition, bringing up the issue. Are we getting prepared to see a devastating cosmic explosion blast that could totally change our evening sky? We should dive into the subtleties inside the enormous breadth of the universe, wherein stars come to life, flourish, and eventually meet their end in a terrific presentation. One huge star has recently caught the attention and trouble of stargazers and the public alike. The enormous star is Betelgeuse, a red supergiant of mammoth extent and advanced age, unmistakably positioned in the Orion constellation. While its exact ruddy tone and varying brilliance have long intrigued observers, recent observations have escalated interest in this celestial giant. As we explore the nature of Betelgeuse, we find ourselves on the brink of a potentially colossal event within the star's life cycle. However, what could these alterations in Betelgeuse signify? Are we witnessing the introduction to an incredibly grand astronomical scene? Betelgeuse, around 764 times bigger than our Sun, remains as a celestial behemoth of immense size, nearly outside human comprehension. Imagine a star so huge that if it were to replace our Sun, its surface could stretch out past the orbit of Mars, enveloping Mercury, Venus, Earth, and Mars in its stellar body. This outstanding size not only highlights Betelgeuse's physical attributes, but also underscores its stage within the cosmic life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, marked by expansion and cooling after a lifetime of fusing hydrogen into helium in its core. Despite being incredibly younger in human terms at around 8 to 8.5 million years of age, Betelgeuse's current red supergiant stage is the result of millions of years of cosmic evolution, transforming from a hot blue star into the red giant we see today. Betelgeuse's extraordinary ruddy hue comes from its cooler surface temperature compared with stars like our Sun. While the Sun's surface temperature is about 5,500 Kelvin, Betelgeuse's cooler surface registers temperatures around 3,000 to 3,500 Kelvin, emitting light at frequencies that give it a red appearance. This hue not only is visible but also provides insights into the star's actual state and the processes within its extensive gaseous envelope. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese texts suggest it was a yellow supergiant around 2,000 years ago, with Arabic astronomers first describing it as red in the 9th century. This color shift over humanity's history provides significant clues about the star's evolutionary path. The variable brilliance of Betelgeuse is equally fascinating, as it is a semi-regular variable star. Its light occasionally waxes and wanes in a natural dance of brightness, following a multi-day cycle and a longer cycle spanning around 5 years. These cycles have been recorded since at least 1836 by Sir John Herschel, and possibly much earlier in indigenous oral traditions. What adds to the intrigue of Betelgeuse is not just its changing brightness but its anomaly. Unlike many stars that follow a predictable pattern, Betelgeuse occasionally deviates from its rhythmic dimming and brightening, indicating complex and less understood processes within its massive structure. In a recent pivotal discovery, Betelgeuse captured the attention of astronomers and stargazers worldwide with a startling and dramatic change in its appearance, widely known as the Great Dimming. In late 2019, the red supergiant star, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to dim inexplicably. The star's dimming became so pronounced that it started losing its brightness at a rate of 0.1 magnitudes per day, reaching its minimum brightness in February 2020. Betelgeuse, typically visible to the naked eye even in light-polluted areas, became incredibly fainter, a change even amateur observers could notice. However, there is a challenge when trying to monitor Betelgeuse's behavior. The time delay means that when we observe a star like Betelgeuse, we are seeing it not as it exists in the present but as it was in the past, due to the time it takes for light to travel to us. For Betelgeuse, around 725 light-years away, the light we see today left the star nearly 7 centuries ago. This delay makes it difficult to predict and uncover sudden changes in a star's behavior, as we are essentially looking into its past. Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team eagerly monitored the unfolding cosmic drama using the Hubble Space Telescope. They observed the massive star as part of a 3 to 12-month study to track variations in Betelgeuse's outer environment. These observations provided unique insights into the behavior of a variable star like Betelgeuse, which frequently expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed scientists to probe the layers above the star's surface, heated partly by the star's turbulent convection cells. Further analysis of the Hubble spectra taken at different points throughout 2019 and 2020 helped measure the movement of material in Betelgeuse's outer atmosphere, specifically focusing on magnesium absorption lines indicative of the star's atmospheric conditions. These observations revealed material moving at velocities of around 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually expanded thousands of miles from Betelgeuse and was the precursor to the dust cloud that caused the star's dimming. Dupree and her team estimated that approximately twice the normal amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the dimming event. This mass loss is particularly significant considering that Betelgeuse, like all stars, continuously loses mass, but at a rate far greater than that of our Sun. The nature of this mass ejection and the subsequent dimming sparked discussions among astronomers about whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, around 725 light-years from Earth, adds to the interest, as such an explosion might be observable from Earth and provide a unique opportunity to witness a supernova up close. However, the question remains, what does this dimming event mean for Betelgeuse's future? Is it a sign of an impending supernova explosion or merely a notable episode in the star's long life? Several theories have been proposed to explain this surprising change. One common idea suggests a gradual buildup in the supernova explosion mechanism, gaining momentum due to the prevailing belief that Betelgeuse is nearing the end of its life. Another widely discussed hypothesis highlighted the possibility of dust originating from Betelgeuse itself, obscuring our view. Red supergiants like Betelgeuse are known to shed material, and it was proposed that this material could form a dense dust cloud, causing a dimming effect when viewed from Earth. Another explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. To unravel this mystery, a range of observational techniques was employed. Spectroscopic studies found a decrease in Betelgeuse's effective temperature, suggesting that the dimming is likely attributed to a major dark spot on the star's surface. Supporting this theory, it was noted that Betelgeuse's temperature dropped by approximately 170 Kelvin around the time of the dimming, indicating significant surface changes. Observations from Hubble's Space Telescope suggested that Betelgeuse's dimming was likely triggered by a regular ejection of material into space. This material formed a dust cloud that obscured part of the star's surface, reducing the amount of light reaching us from Betelgeuse. The results are significant, challenging traditional understandings that red supergiants shed mass at a steady rate before their explosive demise. Instead, the scale of this ejection suggests a more turbulent and potentially erratic end-of-life phase for these stars. Could Betelgeuse be gearing up for its grand finale, a supernova explosion, within the next few centuries? Ongoing research speculates on the timing of such an event, suggesting it might occur sooner than previously thought. Indeed, within just a few centuries, this supernova could become a reality. Another crucial aspect of the Betelgeuse puzzle is its bow shock. As this enormous star travels through space at approximately 67,000 miles per hour relative to its surrounding interstellar medium, it creates a bow shock similar to the wave formed at the bow of a moving boat. This phenomenon occurs because the star's outer layers interact with interstellar gases and dust, providing intriguing insights into the star's dynamic nature and its interaction with the cosmic environment. Analyzing this bow shock not only informs us about Betelgeuse's current state, but also contributes to our understanding of stellar evolution and mass loss processes. Recent observations of Betelgeuse's new behavior indicate that the star's surface has cooled and become less dense following the massive ejection event, leaving the star in an unstable state even years later. Hydrodynamic simulations suggest a link between the star's convective activities, the mass ejection, and the subsequent pulsation mode changes. This ongoing instability raises questions about the internal processes driving these changes and how they might unfold in the future. Moreover, Betelgeuse's observed mass loss rate is significantly higher than that of many other stars, highlighting a complex set of events surrounding its evolution and behavior. The story,